We have discussed how to confine our carrier signal to the power line. And let's now see how this low power carrier signal, say 10 watts, is injected into the high voltage power line conductor. The coupling capacitor, abbreviated as CC, provides the means for power line carrier coupling. As you know, the value of capacitance is selected so as to provide high impedance to flow of 60 hertz power current. On the other hand, at high carrier frequencies, the impedance is low, so the carrier signal can pass easily into the line. Sometimes the coupling capacitor is supplied with voltage transformer circuits which are tapped off the low voltage end of the capacitor. This provides voltage indication and operating power for terminal equipment at the site. This arrangement is known as a capacitor voltage transformer, or CVT, or even CCVT. However, let's focus our attention on the carrier coupling. The terminal box is often located at the base of the coupling capacitor. It contains the capacitor grounding equipment, that is, the grounding switch, the drain coil, and the protective gap. Let's look at the function of the drain coil. As you can see, it is connected between the coupling capacitor and ground. It has an inductance designed to give low impedance at 60 hertz, but a high impedance at carrier frequencies. So the coupling capacitor is safely grounded by the drain coil. The high-frequency carrier signal is connected to the ungrounded side of the drain coil. This signal will pass easily through the capacitor to the transmission line, but it will be isolated from ground by the high impedance at carrier frequency of the drain coil. In essence, the transmitter voltage signal is applied across the coil between the line and ground. The signal current circulates through the power conductor, out to be captured by the receiver through the coupling capacitor at the far end. This is where only one power line conductor and ground is used to conduct the carrier signal. An alternative scheme may use a phase-to-phase connection. As shown in this schematic, the transmitter and receiver are coupled to two power line conductors at each end. The carrier signal is applied line to line. With this arrangement, the requirement for line coupling equipment is doubled. Let's get back to our carrier accessories as they are known. The drain coil is made of very light wire and therefore cannot withstand high current or survive high voltages such as lightning transients. This is why the lightning arrestor is installed here. It may be a gas tube protector similar to the type used on telephone circuits or on pilot wire protection. Alternatively, the lightning arrestor could consist of a simple spark gap, such as a spark plug. If the drain coil were to fail and become open-circuited, it would open the ground on the coupling capacitor. Full line voltage now appears on the protective gap. This fires and an arcing sound is produced indicating an open drain coil. At this point, the maintenance staff will have to hot stick the grounding switch closed and replace the drain coil and perhaps the gap. The carrier grounding switch connects the signal directly to ground and effectively prevents operation of the carrier system. This could also occur inadvertently due to protective gap failure, such as foreign material bridging the gap. Regular inspection of the carrier accessories is necessary. So now, with our carrier equipment connected to the coupling capacitor, we have a low impedance path for the signal to flow into the line. We would like to have a yet lower impedance at the specific carrier frequency so as to reduce coupling capacitor losses. This is achieved by connecting a tuning circuit between the carrier equipment and the coupling capacitor. This circuit is often located below, or at least close to, the capacitor, and is known as a line tuner or line matching unit, LMU. The simplest type of line tuner would consist of a series inductor sized to give inductive reactance equal to the capacitive reactance of the coupler at the specific carrier frequency, say 150 kilohertz. This would produce series resonance with very low impedance to the 150 kilohertz current. Indeed, if the reactances were perfectly matched, the impedance would consist only of the ohmic resistance of the conductors. However, one single carrier frequency is not usually enough. Quite often we will transmit at, say, 150 kilohertz and receive at, say, 112 kilohertz. In this case, the tuner must provide low impedance coupling at both the operating frequencies. In order to achieve this, the tuning circuit becomes more complicated, with a combination of inductors and capacitances arranged in series and parallel. Remember, parallel resonance provides high impedance at its design frequency, in contrast to series resonance, which provides low impedance. These circuits are often known as filters because they allow only the desired frequency currents to pass. Connections between the many inductors and capacitors are made at the terminal board by metal conductor straps. For this reason, the initial test and tuning is often known as strapping. In yet a further development, the tuning circuit is designed to allow operation over a wide band of frequencies, say 100 to 300 kilohertz. Simplified, the circuit looks like this. The incoming signal passes through a variable inductor in series with a variable capacitance, and then passes through a shunt connection to ground through a parallel resonant circuit. Finally, it goes through another series resonant circuit before the signal connects into the coupling capacitor. The signal input from the carrier is via a grounded coaxial cable, which we have shown grounded at both ends. Some utilities ground only one end. Check your utility's procedure. Invariably, the tuning equipment includes a multi-tapped impedance matching transformer at the input end. This is needed to overcome any impedance mismatch which may exist between the transmission line and the power line carrier equipment. The LMU allows us to provide proper impedance matching during the commissioning stage. For example, suppose the characteristic impedance of the line is 300 ohms, and that of the incoming coaxial cable from the carrier equipment is 50 ohms. The matching transformer taps will be selected to give a 6-to-1 ratio.
But why is this necessary? What would happen if the impedances were not matched? Well, the quick answer is reduction in signal power.
When the signal passes into a part of the system where the impedance suddenly changes, some of that signal is reflected back up the line from whence it came. This reflected power robs us of some of the useful forward power that we want to send down the line. Reflection of a signal can be explained by a simple and familiar analogy. When you shine a flashlight through a glass window, most of the energy passes through the glass. Some, however, is reflected back to you. The reason for this is that the glass and the air have very different optical characteristics, and when the light beam leaves the air and enters the glass, some reflection occurs. In our communications circuit, reflection will occur at any point where a discontinuity in impedance takes place. For example, where a second line is tapped into the transmission line. Under certain conditions, the reflected signal may be in phase with the original signal. It is coming and going at the same time, so producing a standing wave.
This is similar to the vibration of a guitar or violin string. The resonant frequency gives off energy in the form of sound. In our power line carrier system, we do not want any portion of the signal to resonate and give off energy.
If this should happen, the energy would be radiated and therefore lost into space. instead of being transferred down the transmission line. In order to prevent this loss, it is important that impedance mismatch be reduced as much as possible. The LMU taps should initially be set as near as possible to the anticipated value of line impedance, usually about 300 to 400 ohms, and the impedance of the coaxial cable usually 50 to 75 ohms. To fine-tune the settings, you will need special test equipment, specifically a voltage standing wave ratio meter. The meter is usually connected into the circuit between the incoming coaxial cable from the carrier and the coaxial terminal connection on the LMU. A carrier test signal is injected at the appropriate frequency, and the meter measures both forward power and reflected power. The taps are adjusted so as to achieve the minimum value of reflected power. This is not so easy where several transmitters are connected, operating at different frequencies. One way of handling this is to connect the LMU into a dummy resistive load equal to the line impedance and adjust the impedance matching at the carrier equipment for each different frequency.
Make sure you follow the manufacturer's instructions closely. There is an extremely wide range of equipment and a great variety of test procedures. One particular utility company test procedure is indicated in your workbook. Study this carefully, but make sure you follow your company's procedure when conducting this test.
If the VSWR test indicates that there is difficulty in matching the impedances, then we must check out the LMU. First, close the grounding switch, then check the connections inside the unit. Coming down from the base of the coupling capacitor, you should see a single insulated conductor called the lead-in wire. Though this is normally a low-voltage connection, it could rise to line potential if the drain coil fails. The lead-in wire may be supported on insulators or run in PVC conduit.
It may even be run in metallic conduit, but this is not good practice as the capacitance of the wire to ground will be larger in metallic conduit, and this extra capacitance could affect the tuning action of the LMU.
Check the lead-in wire for corrosion, burn marks, or tracking, particularly where the wire comes close to the metal structure or cabinet. Next, examine the coaxial cable. In many companies, this is checked annually as a routine because coaxial cable is much more fragile than most other cables. Sharp bends, nicks, and crushing of the jacket can easily degrade its performance. The connection of the cable to the LMU is sometimes a problem. If a coaxial connector has been used, make sure the connection between the braid shield and the body of the connector is solid. If the connection is hardwired, check for high impedance paths to ground and burn marks between the center and the shield of the coaxial cable.
Okay, now that we have looked at connection of the carrier signal to the power line, it's time to consider the signal itself and look at potential losses.